So we can take a measure of the temperature of the universe, and we have really good evidence that the universe is isotropic and homogeneous. We'll see that we learn a lot more from the cosmic microwave background in the 2000s than just that it exists. But that's not evidence. What I've given you so far is far from convincing evidence for the Big Bang. Some of the best evidence for the Big Bang is a story that is rarely told, and is because it's a bit technical, but I want to tell it, and I think we can appreciate what's going on. So, this is the story of Big Bang nucleosynthesis, and it's interesting. We talked about stars and nucleosynthesis and the R process and the S process and supernovae as creating all the heavy elements, but we never discussed the production of helium. Of course, helium is produced in stars, but we saw that not in a quantity that would significantly alter the sort of cosmic abundance of helium. Where did the 25% of the universe that is helium come from? And this becomes clear in a project undertaken by George Gamow and his student Alpher in 1948. And Gamow's agenda at the time, stellar dynamics was not nearly as well understood as it is today. Gamow's agenda was to show that back in the hot, dense early universe, all of the elements were in fact synthesized, and that the current cosmic abundances could be explained by the Big Bang. So what's the idea? If you go far enough into the past, there was a brief episode in the early history of the universe where temperatures were as high and densities as high as in the interior of stars. So there was fusion going on everywhere, at every position, right here. What is the position that is right here, right now? A long time ago was a part of a very hot, dense plasma where fusion was going on. So fusion was going on pervasively, and Gamow's idea was that this is where heavier elements than hydrogen were created. It turns out that, remember, the crucial step for synthesizing heavy elements was the triple alpha process. The triple alpha process worked in the context of a star that had long enough time to maintain a stellar core at high density for a while. Only very rapid processes work in the context of Big Bang nucleosynthesis, because very rapidly the world cools and dilutes and densities decrease. You don't have a stellar envelope holding things in. But it does correctly predict the helium abundance. Let's see how that works. So here's the assumptions. We're going to assume that reactions maintain status of thermal equilibrium in the gas, this hot dense plasma, in the context of an expanding flat universe. This means that the reactions proceed rapidly enough that before the universe has diluted things away, chemical abundances can adjust. And of course, at some point, this stops. And that is at that point, you sort of freeze in the situation that you have. So let's see how that works. Remember that at high temperature, we have relativistic particles, and the number density of a relativistic particle is simply given by the Stefan Boltzmann law. The energy density of a relativistic gas is proportional to T to the fourth. The average energy of a particle is proportional to T, so the number density of relativistic particles is proportional to kT cubed, and in particular is essentially independent of their masses. On the other hand, at low energy, at low temperature, we have non-relativistic particles, and if you imagine that there are processes that can create all kinds of particles, then you can think of particles as energy states, and just in the way that in a gas with temperature T, there can be a tail, remember, of particles, helium particles, whose speeds are 10 times the average thermal speed, but that's an exponential decaying tail. The similar process holds in creating particles. If you have thermal equilibrium, where there are processes that can create and destroy particles, at temperatures below, where kBT is less than mc squared, the number density of a particle decreases exponentially with the ratio of its rest energy to the thermal energy. Particles that are way massive than more massive than the pervasive temperature are unlikely to be found. And as this exponent approaches zero, you exactly go over to the relativistic mass-independent density. So whose radiation? Well, that depends on your temperature. I remind you of our list of particles. I've slightly increased it from back when we were talking about the sun. You see their charges. And based on their masses, I can tell you that protons, for example, become relativistic at temperatures of about 10 to the 13 K, and this G is that geometric factor, the number of degenerate states that a particle has, that relates how many of these there are to how many photons there are. So that's an extra factor of order 1 in the density. Protons become relativistic at 10 to the 13 Kelvin. What about neutrons? Well, neutrons are a little bit more massive than protons, so they become relativistic at a temperature that is just a little bit higher, 10 to the 13, but the main important difference is that the temperature difference for neutrons to become relativistic is about 1.5 times 10 to the 10 K. Electrons, being much lighter, become relativistic at about 6 billion Kelvin. Neutrinos, as far as we know, are massless. They can become relativistic at any temperature. Certainly a photon, which is exactly massless, is relativistic at all temperatures. It always moves at the speed of light. Muons, intermediate in mass, become relativistic at about 1 trillion K, and another kind of particle called the pion. This is not the right number. The mass of a pion is 140 some, 2 maybe, MeV, and so they become relativistic at about 1.6 trillion degrees. There's 3 different kinds of them with 3 different charges, and this is a relic from an old table. Okay, so there's a collection of particles, and as temperatures increase moving into the past, more and more of them are relativistic. So what has this got to tell us? Conversely, as temperatures cool, less and less of them are relativistic. So let's start at the beginning with a very hot universe with a temperature above 1 trillion Kelvin. Neutrons and protons are marginally non-relativistic. But of all the species that are relativistic, then you have thermal equilibrium. And in thermal equilibrium, as we'll see, the processes of physics do not distinguish particles from antiparticles. So there are as many anti-electrons as there are electrons, as many antiprotons as protons, or almost as many. So there are large quantities of antiprotons and protons, antineutrinos and neutrinos, antimuons and muons, and so on. The ratio between the number density of neutrons and protons is given by the ratio of those two exponentials, which is proportional to the difference of their masses in units of kT, and since the difference in their masses is small compared to the temperature, even though they're non-relativistic, there's about the same number of neutrons as protons. Now, as the universe cools by about a factor of 10, by the way, these temperatures obtained for the first 10,000th of a second after the Planck time. So we're deep into the radiation-dominated era, and all the exciting events occur very early in the history of the universe. By the time temperatures have decreased to about 10 to the 11 Kelvin, muons stop being relativistic. When muons slow down, these muons and antimuons find each other. They annihilate. Most of the muons are gone. Only a small remnant of actual muons survive, the excess muons over antimuons. We'll talk about that later. And the muons are gone. By this time, if you plug into this expression, there's still equilibrium. The number of ratio of neutron number to proton number is about 0.86. And note that neutrons, unlike protons, are unstable. Of course, they decay, but they decay in 15 minutes. Neutron decay is not playing a significant role yet. It will later. As the temperature cools farther, by the time we get to 30 billion K, at a time about 1/10 of a second after the Big Bang, neutrinos, because of the slow rates of the weak interactions, essentially decouple. At this point, neutron to proton ratio has decreased to about 0.6, and by the time you get to 5 billion Kelvin, at a few tens of seconds, electrons are beginning to become non-relativistic. Electrons and positrons annihilate, producing a lot of photons. Notice that the neutrinos are already decoupled. So at the time that the neutrinos decoupled, of course, neutrinos and photons were all strongly interacting. They were two gases that could exchange energy. They had the same temperature. So do we expect a gas of primordial neutrinos, just as there are cosmic microwave backgrounds? Sort of, except that when all these electrons annihilated, electron and positron produce two photons with energy 511 keV each. And so this produces more photons, heating the photon gas, injecting energy into the photon gas that is then rethermalized. And for that reason, the photons at that point are hotter than the neutrinos. From that moment on, after recombination, photons evolve the same way as neutrinos, they remain black body, and their temperature decreases with the scale factor. So the ratio between photon temperatures and neutrino temperatures was sort of implanted at the time of electron annihilation, and the neutrinos are colder than the photons by about a factor of 1.4. So there's less energy in neutrinos than there is in photons, but there is definitely an ambient cosmic neutrino radiation flying around. But that's not what we're about. We're talking about the neutrinos, about the neutrons and the protons, because that's what it takes to make helium. Notice that unlike in the present universe you mostly find protons. Neutrons only exist in nuclei. That's because they've had billions of years to decay. Free neutrons do not exist. At these short times, neutrons have not decayed yet. Now, back when the universe was hot and dense, the protons and neutrons are in chemical equilibrium. There are these rapid reactions that can convert neutrons to protons and protons to neutrons in the presence of this sea of electrons and neutrinos. As the temperatures cool and the neutrinos decouple, and soon thereafter most of the electrons and the positrons disappear, these reactions slow down. By that time, the neutron to proton ratio is decreased to about 0.22, because at this temperature the mass difference is significant. It's e to the minus 1.5. Now, notice that once this ratio is achieved and temperatures have decreased, this ratio is frozen in, essentially, because reactions converting protons to neutrons and vice versa no longer take place. So from this moment on, these are the neutrons that you have. Now, so now you have a gas of neutrons and protons, and of course over time the neutrons decay, so you have less and less neutrons. However, the universe is cooling and expanding and cooling, and when temperatures cool down to about 1 billion Kelvin, that's at a time of about 180 seconds after the Big Bang, deuterium is stable. So if a proton and a neutron happen to be moving slowly enough next to each other and bind to form deuterium, deuterium will not be blown apart, photodisintegrated by high energy photons once the energy of the photons is less than 1 billion Kelvin. So until that time there was no deuterium, because if deuterium formed, it would have been blown apart by a photon. After 180 seconds after the Big Bang, deuterium can form. Now, at this point, essentially all of the neutrons that are left form deuterium. How many neutrons are left? Well, I had a fraction of about 0.223 of neutrons to protons, but 180 seconds have gone by. The half-life of a neutron, these are free neutrons, is about 600 seconds. You plug that into our half-life radioactive decay formula, remembering that neutrons decay to protons, so it's parent to daughter ratio. The number of neutrons has decreased, protons increased. The ratio has approximately halved. By this time, only about 12% of the baryons in the universe are neutrons. And now, once deuterium is stable, a neutron inside deuteron is stable, neutrons stop decaying. Essentially all of the remaining neutrons are bound up in deuterium, and very rapidly thereafter they form the very stable alpha particle nucleus. So essentially all of the neutrons that survive produce helium. And so we get left with helium nuclei and free protons, and no more neutrons. So what does this predict about how many helium nuclei you will have formed? Well, we can figure it out. How many of the nuclei that we have left are helium nuclei? Well, each helium nucleus requires 2 protons, 2 neutrons. Since we had this many neutrons, this was our neutron to proton ratio, divide that by 2, that's sort of a count of how many neutrons, how many helium nuclei were created. How many particles? What is the total number of particles? Well, we had sort of the total number of neutrons plus protons, add that up to 1, but then each formation of a helium nucleus took away 2 protons and took away 2 neutrons. So this many helium nuclei took away 4 particles, replaced them by 1, so each helium nucleus reduced the number by 3. Plug in these numbers, you find that 7.5% of all the particles that are left in your, all the baryons that are left are helium nuclei, and of course the others are protons. And any free neutrons that were left around that did not get sopped in will rapidly, within a few minutes, decay, and so you'll end up with protons and alpha particles. That's all you'll end up with. So this is the fraction of the universe that you predict by this very rough calculation will be helium. And in terms of mass, since the mass of a helium nucleus is 4 times the mass of a proton, the mass fraction of helium that you predict is about 30%. This is not bad. Remember, what we observe is about 1/4 of the mass of the universe is in helium. This very rough calculation produces a result that is very close to correct. A more refined calculation produces agreement. Notice that since essentially all I needed to know was the ratio of neutrons to protons, it's very insensitive to details. The rate at which the universe cools, it's a radiation-dominated universe, that has to do with the density of photons in the universe, which I know because I measure the cosmic microwave background radiation. I know the energy density in the thermal microwave background today. I can extrapolate that by energy conservation back to those times. There's very little ambiguity. There's no free parameters. And then that sets the time rate for all of these reactions to occur. And basically nothing depends on any of the details. The fraction of the universe, the protons and the neutrons that are converted to helium atoms, is a very robust prediction. Okay, so we can understand where helium came from. But about other nuclei, remember gamma was trying to produce all nucleons, all nuclear species. It turns out that fusion to heavier nuclei than helium is very inefficient, but you form some small fraction of trace amounts of lithium, and excitingly a little bit of helium-3, and excitingly a small fraction of deuterium. So some of the deuterons did not fuse to form helium, and how many of them did not fuse to form helium depends on the speed with which the universe expands, driven by, remember, the density of the photon gas, relative to the density of nucleons, because the denser nucleons are, the more rapid nuclear reactions are. So the abundance of deuterium is very sensitive to this ratio of the density of baryons to the density of radiation. And since today's density predicts the density then, you can put constraints on the baryon density relative to the density of radiation, which, remember, is known because this is basically sigma times 2.7 K to the 4th over 2C. I know this. Well, this is rho radiation at current time. The background radiation gives me omega R precisely. So this gives me great strong constraints on the baryon density. This, in a sense, tells us two things. One is it tells us that not more than 5% of the total energy of the universe, or of the critical density, could possibly be baryons, else we would have been left with lots more deuterium. And I should point out that there are very few processes after the Big Bang that are likely to form deuterium without producing alpha. This is a process of nuclear physics. And furthermore, it tells us that so that if we find that the density of dust, of matter, non-relativistic matter in the universe, is larger than that 5%, then the remaining amount must be non-baryonic, and therefore this is the 25% of the universe that we think is composed of dark matter. This is one of the strongest constraints. You can, of course, do some more refined calculations that take into account both the concentration of helium and of various isotopes, and, as I said, the trace amount of lithium that was produced. And so this gives us a constraint on cosmology. Moreover, if you tweak your model of particle physics by all kinds of additions to the standard model, trying to understand, as we will see, theories beyond the standard model, they might make small modifications to the rates of these nuclear reactions. Things are extremely sensitive to the rates of nuclear reactions. For example, you can do a rather straightforward calculation that shows that if there were more than three, remember there were three species of light neutrinos, the mu neutrino, the electron neutrino, and the tau neutrino, more than three species of light neutrino would lead to unacceptable, to deuterium concentrations that are incompatible with observation. And so, in that sense, we know there cannot be a fourth, as yet undetected, neutrino species, because it would ruin Big Bang nucleosynthesis, a very sensitive test of our understanding both of cosmology and of particle physics, and one of the great successes of Big Bang cosmology.